Hello, we begin the third part of this course, semiconductor devices. We will discuss four topics: metal semiconductor contact, Schottky diodes, as part of the metal semiconductor topic. Then we will go on to MOSFET, metal oxide semiconductor field effect transistors. Then we will um, see how semiconductor diodes, p-n junction diodes work. And finally, we will look into optoelectronic devices such as solar cells, light emitting diodes, and semiconductor lasers. So that's the plan. In the metal semiconductor contact, we need to figure out two things. The first one is how the electrons and holes get distributed in space in the vicinity of the contact. What happens to the semiconductor bands in the vicinity of the contact. And second is what is the current voltage curve of a metal semiconductor diode, also known as Schottky diode. So in the first lecture, I will show you how this energy band diagram tool can be used to analyze the metal semiconductor contact. I will discuss the two types of contacts, ohmic and rectifying contacts. And finally, I will show you how what quantum tunneling is and how it can be used to produce an ohmic contact. So let's begin with the energy band diagrams. Interesting. So far, we have discussed standalone semiconductors. A single piece of semiconductor is not very useful for practical applications, but interesting things may happen if you combine either semiconductors that are doped differently, in particular p-type and n-type semiconductors, or if you combine a semiconductor with a metal. And then you really can build devices that can have practical applications in electronics. So let us begin with the energy band diagram of a metal semiconductor contact. What is a metal? It is an object where atoms are arranged periodically. As a result, electron energy levels belong to bands, Bloch's theorem. And the Fermi energy is in the middle of one of those bands. So this is the more detailed view of a metal energy band diagram. Here is one band which is completely filled, and here is another band which is, let's say, half filled with the Fermi energy in the middle. And this is the simplified view of that piece of metal, where you do not care about this band gap that separates the completely filled band from the partly filled band. It's just irrelevant because the completely filled band does not play any role. Now, of course, this shaded area in the energy band diagram indicates that the states with the energies below the Fermi energy, like here, the shaded states, so to speak, are filled with electrons. In, I believe, our first lecture, I have already introduced the concept of the work function. This is the energy, the minimal energy that you need to give an electron in order to bring it out of metal, and it is close to metal, but outside of the metal, and it finds itself in the state of rest. So we need to introduce this vacuum energy. The energy of the electron just outside of the metal at rest is the vacuum energy. This is what we will call it. And the energy difference between the Fermi energy and the vacuum energy is the electron work function. We will denote the work function with the letter psi, not to be confused with the wave function discussed in the context of quantum mechanics. So here in this part of the course, psi will be the work function. And it is measured in volts. right? So the energy is the product of the work function, the energy needed to kick out an electron into vacuum out of metal is the product of the elementary charge E and the work function psi. And it is minimal because electrons in metal um, have so the Fermi energy is not the highest energy that electrons can have, but the highest energy that electron can have in metal is maybe above the Fermi energy by one or two thermal energies. Thermal energy is small. All right, so that's our metal energy band diagram. Now, what about the semiconductors? Okay, so in this case, we have an n-type semiconductor. How do I know that it is an n-type? It's because the Fermi energy is closer to the conduction band. It is in the upper half of the band gap. The states in the valence band are predominantly occupied. Some states in the conduction band are occupied, but the concentration of electrons in the conduction band is relatively low. Again, the work function of the semiconductor is denoted as E psi sub s, and it is defined as the energy difference between the vacuum energy, that is the energy of an electron just outside of the material, and the Fermi energy. So that's the definition of the work function of the semiconductor. The work function of a metal is fixed because the Fermi energy of the metal is fixed. It is simply the number of, it is determined by the number of electrons per unit volume in the metal. And as for semiconductors, Fermi energy is not fixed. It depends on the level of doping. But the fixed parameter, the fixed energy scale in a semiconductor is the so-called electron affinity. It is the energy difference between the vacuum energy and the energy at the bottom of the conduction band. Electron affinity cannot be controlled by doping the material. And the work function is like by geometrically, the work function is electron affinity, which is denoted with the letter chi. Again, chi electron affinity is measured in volts, and the energy is the product of the elementary charge and chi. E chi is the electron affinity. So the work function psi semiconductor is electron affinity plus the difference between the conduction band edge and the Fermi energy, and this energy difference can be expressed in terms of the concentration of electrons in the material. All right. Now, these energy band diagrams were plotted under the assumption that semiconductor and the metal are not in contact. You have one piece here, one material there, and they do not know about each other's existence. Now you put them in contact. Then several rules need to be kept in mind to draw the energy band diagram of the metal semiconductor contact. One rule is that eventually the two materials will come into chemical equilibrium with each other, or the particle equilibrium with each other. Electrons will migrate from metal to semiconductor or from semiconductor to the metal, depending on the relationship between the work functions of the two materials. But eventually, very quickly, it's really a matter of, I do not know, picoseconds, maybe nanoseconds, the Fermi energies of the two materials will align. And that happens when the two materials come into equilibrium with each other. So the Fermi energy of the two materials in equilibrium must be the same. The second statement that I would like to make is that the vacuum energy, now the work functions of the semiconductor and the metal are not necessarily the same. In general, they will be different. You need to work really hard to select that correct level of doping to make the work function of a semiconductor match the work function of a particular metal. So but the work function is the difference between the vacuum energy and the Fermi energy. And that means that the vacuum energy, since the Fermi energies are aligned with each other, the vacuum energies must change in space. This may seem a little bit counterintuitive, but it's not. It simply means that there will be some sort of a potential difference between the metal and the semiconductor. Some sort of a small potential difference will develop. And that voltage, that potential difference between the two materials results in the bending of the semiconductor bands. In particular, it also, since all these parameters, such as the conduction band energy, the vacuum energy, valence band energy, must remain in the same relation with each other. That is, the important energy differences, such as the EC minus EV, the band gap, the difference between the band edge energies in the conduction and the valence band. The electron affinity, that is the difference between the vacuum energy and the energy at the conduction band edge. All these energy differences must be the same. So the band bending in the semiconductor must be the same for all bands and also for the vacuum energy. The vacuum energy must be a continuous function of space, because if it were not a continuous function of space, then this would imply that an infinite force, like if the vacuum energy had a discontinuity at the interface, then at the point of this discontinuity, this would mean that there is an infinite force, infinite electric field between the two materials. But that's physically impossible, because infinite electric field implies also infinite electric field energy density. So this is impossible from the energy point of view. The discontinuity of the vacuum energy is physically impossible. All right. So and this means that the semiconductor bands must bend, which again, which is due to the fact that there is a potential difference between the metal and the semiconductor, and that potential difference changes as you go further and further away from the interface with between the metal and the semiconductor. The sign of the band bending depends on the relationship between the metal and the semiconductor work functions. So if the semiconductor work function is greater than the metal work function, then the semiconductor bands will be bent down, so to speak. So they here in this figure, the bands are bent up, but if the bands are bent down, then they go like what the cursor does here. So let's say this is the vacuum energy, steady, 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 and then it goes down. That's if the semiconductor work function is higher than the metals. And if the semiconductor is smaller than the metal's work function, as shown in this figure, then the semiconductor bands are bent up. You may wonder what happens to the metal bands. Why do not they exhibit bending? And the answer is because the concentration of electrons in a metal is much higher than the concentration of free charge carriers, electrons and holes, in the semiconductor. So the spatial extent of the band bending is of the order of can be estimated using the Debye debye length formula, it is inversely proportional to the square root of the charge carrier concentration, the Debye formula. So if the semiconductor concentration of charge carriers is much smaller than the metal's charge carrier concentration, then the spatial extent of the band bending in the semiconductors would be much bigger than in the metal. So the band bending in semiconductors is much more visible than in the metal. There is some band bending in the metal as well, but its spatial extent is so tiny that it may be neglected, and it is really hard to show in the diagram. It is orders of magnitude smaller than in the metal than in the semiconductor. So we have 4 possible combinations. The semiconductor can be either of N or of P type. That's 2 combinations. And the semiconductor work function can be higher or lower than the metal's work function. 2 times 2 gives us 4 possible combinations. If the semiconductor is of N type and the semiconductor work function is lower than the metal work function, then in order to keep the vacuum energy continuous, the semiconductor bands must be bending up. It is N-type. Fermi energy is closer to the conduction band energy. The semiconductor bands must bend up in order to match the vacuum energy in the semiconductor and in the metal at the interface between the 2 materials. If the semiconductor is of N-type, but the work function of the semiconductor is higher than that of the metal, then the semiconductor bands must bend down. And this is this situation in the second diagram from on the bottom, in the bottom part of the figure of the slide. In the former case, N-type semiconductor, the work function is smaller than in the metal. The contact is rectifying. In the latter situation, the contact is ohmic. How do we know if the contact is rectifying and if it is ohmic, and what is ohmic contact and rectifying contact in the first place? So the rectifying contact is the one that exhibits diode effect. That is, if you apply forward bias, then you will get high current. If you apply the same bias but in the reverse direction, then you will get low current. If the metal work function is higher than the work function of the N-type semiconductor, the semiconductor bands are bent up. This implies that there is a depletion region in the semiconductor right near the surface, right near the interface with the metal. Because notice that near the interface, the Fermi energy is further away from the conduction band edge energy from here than in the bulk of the semiconductor, right? So this means that the region right near the interface between the metal and the semiconductor is depleted on the semiconductor side. This region is depleted of the majority charge carriers, of the majority electrons. Now, if I apply positive bias to the metal, then I will make this depletion region smaller. I will make it easier for the electrons to go from the semiconductor to the metal. Okay, so my majority carriers are electrons. I am applying positive bias to the metal. I make it easier for electron. I am reducing the size of the depletion region. Also, I am reducing the size of the band bending, because then the vacuum and the metal energy levels will go down if I apply a positive bias to the metal. And I will be reducing the size of the band bending. I will making it easier for electrons in the semiconductor to overcome this barrier, and make it into the metal. I can expect that the current will be high if I apply large positive bias to the metal. Now, if I apply a large negative bias to the metal, I am pushing away the majority electrons in the semiconductor. I am pushing them away from the interface with the metal. As a result, this depletion region will grow in size. In principle, I can make the biases so big that I will form an inversion layer. Anyway, when I apply a negative bias to the metal, I am pushing away the majority carriers on the semiconductor size. I am increasing my depletion region. I am increasing the barrier that prevents the electrons from the semiconductor to enter the metal. Of course, the barrier that prevents electrons from the metal to enter the semiconductor will remain unchanged. This energy difference. It is the difference between the maximal value of the conduction band energy in the semiconductor, that is here at this peak, and the Fermi energy at the metal. No matter how big my negative bias I am applied to the metal is, this energy barrier, the so-called Schottky barrier, will not change, or practically will not change. But since this Schottky barrier is so high anyway, maybe 1 electron volt or so, the current from metal into the semiconductor will remain very small. So I have positive current in the forward direction when I am applying a plus to the metal, and I will have a small negative current in the reverse direction, which practically does not depend on the bias when the bias is negative, when I am applying a minus to the metal. Hence, this contact is rectifying. Now, in the ohmic contact situation, again, the semiconductor is of n-type, but the work function of the semiconductor is higher than the work function of the metal. If I apply plus to the metal, that is, I am attracting the electrons from the semiconductors. The electrons live in the conduction band, so they will have to go left, left, left. Then they see like some sort of a slide. They have to travel downhill, and they make it into the metal. If I am applying minus to the metal, then I am pushing the metal electrons into the semiconductor conduction band. And since this energy barrier is not particularly big, it is still quite easy for the metal electrons to make it into the conduction band. Now you may ask, what is the role of the valence band in this ohmic? And so the contact will be ohmic. And you may ask, what is the role of the valence band in this ohmic contact? The answer is practically non-existent, because the vast majority of the states in the valence band are occupied if your semiconductor is of n-type. The valence band doesn't have empty states, so it doesn't contribute to conductivity, to current flow. Only the conduction band does. All right, now let's look at the p-type semiconductor, and again, let us discuss two situations when the semiconductor work function is higher and lower than the metals. And here the distinction between the ohmic and the rectifying contacts is reversed. So if the semiconductor's work function is bigger than the metal work function, then the contact is rectifying. And this is what happens. Now my semiconductor is of p-type. So the conduction band does not contribute to conductivity, to current production, because it is empty. practically empty. Well, not completely empty, but the concentration of electrons is much, much, much lower than the intrinsic concentration, which in turn is much, much, much lower than the concentration of the holes in the valence band. Now, if the semiconductor work function is higher than that of the metal, then in order to maintain the continuity of the vacuum energy, the semiconductor bands must bend down, as shown in this diagram, upper right diagram. All right, so why is this contact rectifying? Let's see what happens if I apply a positive bias to the metal, plus to the metal. As I am applying a positive bias to the metal, I am pushing away the majority holes, which are positively charged particles, from the metal semiconductor interface. And simultaneously, I am kind of preventing the electrons, the metal electrons, from entering the semiconductor. So, since I am pushing away the majority carriers on the semiconductor side, and I am not letting the electrons of the metal to enter the semiconductor, I will have very little current. Some current will still be flowing, because the current is always flowing. Well, maybe it will be a very small, tiny current, but it will be flowing in the presence of some bias. But the bias is positive. If the bias is positive, then some electrons will be able to enter the metal from the semiconductor side. But in order to enter the metal, these electrons would need to overcome this energy barrier. Right? See, they cannot enter the metal from the those electrons in the semiconductor, they belong to the valence band. And they live near the top of the valence band, because near the top of the valence band you have those empty states, holes, right? So you're attracting those electrons that travel along this line, curved line at the top of the valence band. At first, they easily reach the metal semiconductor interface, but now they need to overcome this energy barrier, because they have to enter the metal and end up at the energies of the order of the Fermi energy, so somewhere at the Fermi level. Okay, so this energy barrier is again called the Schottky barrier for the metal p-type semiconductor contact. Some electrons will be able to do that. So there will be a small current for positive voltage applied to the metal relative to the semiconductor. Now what happens if I am applying the negative voltage to the metal? This is what happens. I am pushing the electrons on the metal side. I am pushing the electrons toward the semiconductor. Simultaneously, I am attracting the holes on the semiconductor side, because I am applying negative bias, right? So I am attracting the positively charged quasi-particles, holes, from the semiconductor side toward the metal. And now you have two armies. An army of electrons running from metal to the semiconductor, and an army of holes running from the semiconductor toward the metal. And they meet at the interface, and they mutually annihilate. They recombine. Okay, so this picture with two armies which mutually annihilate is poetic. You can also think of it as electrons move from the metal into the semiconductor. They end up in the valence band of the semiconductor, which has plenty of empty states, and they keep moving. They keep moving away from the interface, so to the right on the energy band diagram. So Anyway, whatever picture you adopt is okay. Um, the moral is that the contact with the of a p-type semiconductor with the metal is rectifying if the semiconductor work function is higher than the metal work function. However, you will have large current for negative bias if the semiconductor is of p-type, and large current for positive bias if the semiconductor is of n-type, like this rectifying contact in the left, in the upper left diagram. All right, finally, let us consider the situation when the semiconductor is still of p-type, but the work function of the semiconductor is smaller than that of the metal. In that case, the band bending in the semiconductor is up. The bands are bent up. I apply positive bias to the metal. I will be attracting the electrons from the valence band into the metal. They do not need to overcome a huge barrier. There will be some small barrier. So you can have a situation when the semiconductor valence band is actually degenerate near the interface, like in this diagram. It's okay, it is possible. There is nothing unphysical about it. So the Fermi energy may end up within one of the bands, like the valence band in this case, due to the difference between the metal and the semiconductor work functions. So if I apply the positive bias to the metal, I will be attracting the electrons from the valence band into the metal, and the current will be high. If I am applying a negative bias to the metal, then I will be pushing the electrons from the metal into the semiconductor. The current will be high. So this will be ohmic contact. The reason why I need ohmic contacts, I forgot to tell you, but only because I thought it was like kind of, it is an obvious reason. When you have, if you are trying to produce some sort of an electronic device with diodes and transistors and amplifiers and other semiconductor-based components, then you need to communicate with those semiconductor parts of the device. And for that, how do you communicate with them? Well, you need to use metal wires. And so, of course, you need to produce a contact which would allow the current to flow both for forward and reverse bias with as little contact resistance as possible. And so that's why you need ohmic contacts. Go to ohmic contacts. So there is another way other than doping. Well, there is another way to produce an ohmic contact other than choosing the materials with the right value of the work function. So let's say you know that your semiconductor is silicon with such and such doping level, then what kind of metal should I use? Okay, so the second possible way to produce an ohmic contact between a metal and the semiconductor is based on the quantum tunneling effect. Quantum tunneling is a real effect. So it does happen, and it also happens in everyday life. In the alpha decay reactions, well, alpha decay reactions do not happen particularly often in everyday life, but they do happen. So alpha decay reactions is when a heavy nucleus emits an alpha particle and becomes a little bit lighter. Alpha particle is the doubly ionized helium-3 atom at the nucleus of helium-3, 2 protons and 1 neutron. So quantum tunneling, the physics behind quantum tunneling is simple. Let's say you have an electron and it is incident on some potential barrier. Right? So there is a potential barrier. It has some finite width and a finite height. If the energy of that electron is smaller than the height of that barrier, then classical physics tells us that the electron or whatever particle it is will get reflected by the barrier. Yeah? like a ping pong ball against the wall, gets reflected by the wall. But if you take into account the wave nature of particles, then the wave function, when at the contact with the barrier, at the position where the barrier is, the wave function of the electron cannot go immediately to zero. It will decay quite quickly into the barrier, but it does not go to zero immediately, because nature doesn't like it when things change immediately. Nature doesn't like these sharp transitions. So the wave function will decay into the barrier, but on the other side of the barrier, the wave function will be low, but not completely zero. And that means that the probability to find an electron on the other side of the barrier remains finite. This is the quantum tunneling effect. How can we apply quantum tunneling to produce an ohmic contact? So you have, let's say, a metal and the semiconductor, and here the semiconductor work function is smaller than the metal work function. So previously here we had the semiconductor, N-type semiconductor with the work function higher than the metal and the metals, and that was ohmic contact. But now what if the semiconductor work function is smaller than the metal's work function while the semiconductor is still of N-type? So we need to dope to make the semiconductor even more of N-type and plus, that is, we apply very large amount of doping near the interface between the semiconductor and the metal. The semiconductor is highly doped, more heavily doped near the interface than in the bulk. As a result, we have three regions: the metal, the highly doped semiconductor region, and the weakly doped semiconductor region. Now, the heavily doped semiconductor region behaves as practically a metal because the concentration of electrons, the majority electrons here, is large. And this heavily doped semiconductor region is in contact with the moderately doped semiconductor region here. And this contact is ohmic. This contact is ohmic because the semiconductor bands, the bands of the N-type semiconductor here, are bent down. So here we have an ohmic contact. What about the contact between the metal and the heavily doped semiconductor region, this N+ region? The semiconductor bands are bent up. Is this a rectifying contact then? By classical considerations, the answer would have been yes, because there is the Schottky barrier. There is the Schottky barrier. But if we take into account the quantum nature of electrons, and notice that the Schottky barrier is, yes, it is high, but it is also very, very, very narrow. Then electrons can easily tunnel through that Schottky barrier. And so the band bending here plays very little role. It is like as if the Schottky barrier were not present at all. So now the electrons can easily tunnel through the Schottky barrier between the metal and the heavily doped part of the semiconductor in the interface, making this contact ohmic again, not rectifying, but ohmic again. Nice, isn't it? So that's all that I wanted to tell you in this. It looks like it has been a brief lecture, Thank you all very much for your kind attention. I'll see you in the next lecture. Bye-bye.